Let's start talking about conic sections. And a conic section is simply the intersection of a plane and a double napped cone. So I've given a couple of examples of such types of conic sections here. And so you can imagine that there is a hollow cone, or I should say two hollow cones that are joined together at their point. We call that a double napped cone. And so if you envision or can kind of imagine a plane as being part of a really, really large sheet of paper, if you will. And in fact, this sheet of paper is actually going on infinitely in all directions. But if you imagine like this sheet of paper or piece of cardboard, if you would, intersecting or slicing through this plane, depending on how that plane intersects through this double napped cone, we have a different type of conic section. So if you imagine that that plane or that piece of paper is intersecting through one of the two parts of the double napped cone at exactly the same angle as the opening of the cone, then you would have a circle. If you go on to this next part, if that plane is now intersecting one of those parts of the double napped cone at an angle, or I should say at an angle that is not the same as the opening of that cone, then you have kind of like a stretched out circle, if you will, or an ellipse. And then if we go on, you can see that if we cut through part of the cone, we have a parabola. And if our plane then cuts through both parts of the double napped cone, then we have an hyperbola. Now, in the context of our course in pre-calculus, we're going to be working with most of these conic sections in the context of a Cartesian plane, or I should say a rectangular two-dimensional plane, kind of an XY plane. And so we won't really look at it from this perspective, but this is just to kind of illustrate to you what a conic section exactly is. And we'll go into some more formal definitions in a bit. I do want to bring up briefly that there are things called degenerate conics, and these aren't just conics that are really immoral or anything. These are just different types of conic sections, like if that plane were to intersect the double napped cone at exactly the point where the two parts of the cone are joined, or in such a way that it would be exactly along the edge of one cone and along the other opposite edge of the other, then you would have a line. So a point, a line, and also a plane that goes right through and creates two intersecting lines. These are all known as degenerate conics. And we've already worked with points, lines, and intersecting lines in this course before, so we're not going to spend too much time talking about those right now. But we will focus primarily on these four conic sections in this course: circles, ellipses, parabolas, and hyperbolas. So what is the general form of a conic section? The general form of a conic section is as such, and I'll just go ahead and paste that here. I wrote it ahead of time. Let me go through a couple parts of this. So the general form of a conic section is written out as follows: ax squared plus bxy plus cy squared plus dx plus ey plus f is equal to 0. Now, I know that seems kind of daunting at first glance, but every conic section that we're going to work with is going to have a different form of this. In all of them, we typically will see that b is usually equal to 0 in the ones that we work with. Usually b will be equal to 0, so we're not going to typically have to worry about that one. So you can even erase that over here and just move to that. But I'll leave it in there just so we can see the general form. And while this looks kind of like a lot at first, every conic section has different values for these coefficients, so that we just need to worry about those specific forms for those conic sections. Let's start today by talking about circles. And a circle is the set of all points in a plane that are equidistant from a fixed point, also known as the center. So I went ahead and I drew a circle for you here, but let me just kind of break down, make sure we understand how to define a circle in the context of our understanding of conic sections. So if we have a point, and I'm going to call this point the center here. And in a moment, we'll see that that center can also be written in terms of these coordinates h and k. And I won't go into that just yet. But if we have a center there, then we would say that every single point that is equidistant to that center. So for example, if I were to measure the distance from that center to this point out here, and let's just call this point here like x, y, and we'll call this distance here from the center to that point the radius. every single point that has that same radius. So if I were to draw another point out here, okay, so this is a separate point like P2, and we'll call this X2, Y2. But if that distance from the center to that other point is also the same, all the points that we can draw that are equidistant to our center forms what we call a circle. And that shouldn't be too new to us. I mean, we've already talked about circles in geometry, but in the context of a conic section, it's the set of all points in our plane that are equidistant from a fixed point, the center. And the radius is, again, just the distance from that center to any point on the circle. So what if I wanted to find that actual distance? Well, if I wanted to find the distance for our radius, how do we find the distance of any line segment? Well, we just use the distance formula. So if I were to write that in the context of what we have here, and I'm just going to go ahead and erase one of these just so that we're not too confused. If I were to go ahead and find the distance between that point and the center, we would say the following. We can say, in general, x2 minus x1, that quantity squared, plus y2 minus y1, that quantity squared, gives us the distance of any line segment. This is the distance formula, which is derived from the Pythagorean theorem. Now, in the context of what I have written here, if we use h and k to define the coordinates for our center, and again, x and y for any point that's on our circle, we can then rewrite this distance formula using what we have inside the circle. So x minus h squared plus y minus k squared. And this is going to give us the formula for the radius. So the radius, that distance can be measured as such. Well, what were to happen if I were to then go ahead and square all this? Well, if I were to square all this, look at what we have here. We would then say r squared is equal to the square of a square root is simply that negated, so we just have x minus h squared plus y minus k squared. And what do you know? This is what we know to be the general form of the circle. You probably have seen this before, but again, just to write it out here, this is the general form of a circle, where again, C is going to be defined as our center, which we use h and k typically to denote the coordinates for the center. And any point on the circle, we're just going to usually describe as x and y, okay? So this is the general form of our circle here. And when we are dealing with a circle whose center is at the origin, then all that means is h and k are both going to be equal to 0, and I'm leaving off an exponent here, sorry about that. Again, when our center is centered at the origin, that means our h and k are both equal to 0, so we would typically then just write the following. This is when the center is at 0, 0, okay? All right, so now that we know the standard form of our circle, let's go ahead and let's work through a couple of problems where maybe we're given the standard form or we're given information about the circle and we need to come up with the standard form. All right, so let's try this first example here. So the standard form equation of the circle that passes through 1, -2 with the center at -3, -5. Typically when I work through conic questions, I like to just label all the given information from the get-go. So if I know that this is my center, I know that this is going to be my h and this is my k. And if I'm given some point on the circle, we're told that the circle passes through this point, so it must be a point that lies on the circle. That means this is my x and this is my y. Well, at this point, just plug in whatever you know about this circle into your standard form equation. Well, we can say the following. We can say, well, when x is 1, we can say 1 minus h is -3, so -3, and that quantity is squared. My y is -2 minus, and my k is -5, that quantity is squared, and we don't know our radius, so we're going to need to square that. But based on what we've plugged in, we're actually finding our radius through this information. So we would see that 1 minus -3, that's 4 squared, plus -2 minus -5, that's 3 squared, and that's equal to r squared. So r then is equal to 5. Or let me write this first. R squared is equal to 25. That means R is equal to 5. Now that I know my radius, I can write my standard form equation. I know that it's always going to be x minus my h and my x minus h, so x plus 3 squared, plus y minus k, and since k is negative 5, I'm going to say y plus 5 squared, and all of that is equal to 25. If you want to write that as 5 squared, that's totally fine as well. So here is the standard form equation of this circle based on the given information. All right, let's try another problem now. This time, let's go ahead and let's find the standard form equation of the circle based on this equation that is given to us. So we're given the equation here, and what we need to do is we need to rewrite this in standard form. Now, later on in the course, we're going to be given equations like this, and it's not going to be explicitly told to us whether or not it is a circle or a hyperbola or some other conic section, but we'll get much better as we go along with kind of determining what type of conic section that is based on the coefficients and whether or not values are positive or negative. Now, take a moment and ask yourself, based on what I'm seeing here, how would I be able to tell right off the bat that this is a circle? Well, if we compare this equation to what I gave you early on, we see that with standard form equations of circles, we see that A and C are both equal to each other, and they're both equal to 1. Therefore, this tells me it's a circle. Now, how would I write this in standard form? And the answer is we are going to need to complete the square. So we're going to complete the square. If you remember how to do that from your algebra course. So let's think about this. Let's take this equation. Let's write. I'm going to group together my x's and my y's separately so that I know how to complete the square for each one of those variable terms. So we have x squared minus 2x, and I'm going to need to add some value here in a moment to complete that square. Next up, we've got y squared plus 4y, and we're going to need to add some value to that in order to complete the square. And I'm going to take my constant here, which was -4, and I'm going to move it to the other side. I'm going to put all my constants together. That way, when I'm completing the square, I can add up everything that I've added over there on that side. So if you remember how to complete the square, we're going to need to take half of this value, right? So since this is our b here, we're going to take half of our b value. So we're going to say b over 2, okay? Or I should say here, this is my b value, excuse me. And then here, we're going to want to take half of that b value, and then we're going to need to square it. So half of -2 is -1. -1 squared is +1. So again, half of -2 was -1. -1 squared is +1. Because I added a 1 there, I'm also going to be adding a 1 here. That way I'm keeping my equation equal on both sides. Now let's rinse and repeat with y squared. What is half of 4? Half of 4 is 2. 2 squared is also 4. And again, I'm going to add that value to this side as well. So now that I have that, let's go ahead and let's write this here in factored form. So x squared minus 2x plus 1, that would be x minus 1, that quantity squared. Now let's group together the y polynomial. So y squared plus 4y plus 4, if we write that as a square, we would say that this is y plus 2 squared. Now on the right-hand side with all my constants, let's add all those up. -4 plus 1 plus 4, that's simply equal to 1. And, oh, I actually made a mistake there. When I moved that -4 over, I should have added that as +4. I apologize. So that should have been +4 because I'm adding 4 to both sides to move it over there. And that actually then would give me 9. So this here is my standard form of my equation. And then from here, would I be able to identify things like the center or the radius or the x-intercepts? So my center would be h and k, which in this case is 1 and -2. Be mindful of those signs. My radius then, we know is going to be, if this is our squared, then we know our radius is equal to 3. And based on that information, we can actually go ahead and graph this now. So I'm going to go ahead and graph that. So I know my center is at 1, -2. So 1, -2. And since my radius is equal to 3, I'm then going to go ahead and draw in the 4 directions. I'm going to go ahead and I'm going to draw a radius or a distance of 3 from the center. So we know that it's going to be a distance of 3 for every single point on this curve, but this might actually just help me go ahead and do this a little bit easier. Now, students often struggle drawing circles, and I get it. I'm not a great artist myself, but something that I've found that often helps is if you kind of just break this up into quarters and take your time with it and just draw a quarter at a time, you get something that isn't terrible. And this may not look great in your eyes, but for the intents and purposes of what we're trying to graph, that works pretty well. Okay, so there's my circle. The one part I haven't answered yet is how about those x and y intercepts? Well, this is just algebra review as well. How would we find an x-intercept? We know that an x-intercept means y is equal to 0. So you take your standard form equation that you have here and then just plug y for 0, or 0 for y, I should say, into your standard form equation. So we have x minus 1 squared plus 0 plus 2 squared is equal to 9. And then that means x minus 1 squared plus 4 is equal to 9. Cleaning this up here, that should be equal to 5. If I then take the square root of both sides, extract those roots, I've got x minus 1 is equal to plus or minus root 5. And then let me actually just go ahead and continue this over here. Oops, I don't want to move all that. Let's try that again. And so here, I can just say x is equal to 1 plus or minus root 5. Keep in mind, that is not your x-intercept. An x-intercept is a coordinate. So I'm going to write this as 1 plus or minus root 5, comma 0. There's my x-intercept, which again is the place where it's going to cross the x-axis because that's when y is equal to 0. What about the y-intercept now? Well, to find the y-intercept, we're going to set x equal to 0. So we're going to do the same thing here. We're going to say, all right, 0 minus 1 squared plus y plus 2 squared is equal to 9. We then have, that would be 1 plus y plus 2 squared is equal to 9. And let's just actually write that as y plus 2 squared is equal to 8. Take the square root of both sides. Then I'm just going to do this in one step here, but we're going to say y is equal to -2 once I've taken the square root of both sides. -2 plus or minus 2 root 2, which is just a simplified form of root 8. That means my y-intercept would be 0, -2 plus or minus 2 root 2. And there's my y-intercept. And so now we see where it's crossing the y-axis because that's where x is equal to 0. Okay? I now encourage you to try this next problem on your own and go ahead and check my solutions with what we have in Classroom. Good luck.